So this question's fairly similar to the example problem, except that now we've got two positive charges. So we've got a positive charge here at minus d onto 0 and a positive charge here at d onto 0. And halfway between these, we've got the point 0, 0. And in part A, we're asked to calculate the electric field in this region here. So let's just sketch the direction of the electric field. We know that electric field lines go away from positive charges. So due to this one at minus d on 2, it will be going to the right. And due to this one at d on 2, the field between here will be going to the left. And then we'll just need to use the law of superposition to sum up the contributions from each of these charges individually. So let's consider some point which is at a distance x from the origin. So it's just the point x there. And so due to the charge at minus d on 2, we can say that the electric field, because electric fields are given by kq on r squared for point charges, is given by kq, and then we'll need to divide by the distance squared. So we've got the distance between this charge and point x, and you can see this distance here is going to be d on 2, and then we've got the additional x. So this will be d on 2 plus x, and then we square it. And this is to the right. And then the electric field due to the charge at d on 2 is given by, again, kq. But now we've got the distance between the charge, which is at d on 2, and the point x here. So this distance is going to be d on 2, which is this distance, minus x. So we'll have d on 2 minus x, and that's squared, and this one is to the left. And so the total, we'll just need to sum these together. So the positive direction is taken us to the right. So we'll have E minus D on 2 and then minus E D on 2. And so, and this is to the right. So substituting in, we've got KQ over D on 2 plus X squared minus KQ over D on 2 minus X squared. And then we'll want to simplify this. So let's pull KQ out as a common factor, and we'll give it a common denominator of D on 2 plus X squared, D on 2 minus X squared, and then on the top up here we've got D on 2 minus X squared minus D on 2 plus X squared. Okay, so to simplify this, let's expand these brackets, and so we've got D squared on 4 and then 2 times D on 2 times X, so that's minus dx plus x squared minus d squared on 4 and then minus dx and then minus x squared. And then we're dividing by, here we've got difference of 2 squares, so we can write this as d squared on 4 minus x squared squared. And you can see on the top, these x squareds cancel, these d squareds on 4 cancel. Okay, and then we've got our factor of kq, and we've got minus dx minus dx. So that's minus 2 dx times kq. So kq dx divided by d squared on 4 minus x squared squared. Now, the question said before entering our answer, we should check what we expect it to be at 0, 0. So at 0, 0, we are halfway between these two charges. So the electric fields from the two charges should be equal, and we know that they're opposite. So we expect it to be 0 at 0, 0. So if we substitute in x equals 0, you can see that this does become 0. We end up with 2kqd times 0 divided by d squared on 4 squared. So that does go to 0. So it does meet our expectations of what the field should be. So that was part A. With part B, we're then asked to calculate the field out at another point out here. So this distance out here is now x. So and let's just consider the directions out here as well. From this charge at d on 2, that will be heading to the right. And then from the charge at minus d on 2, that's also heading away from it, so it's also heading to the right. So in this region, the electric fields are going in the same direction as each other. And so we can say, well, the electric field due to the charge at minus d on 2 is once again given by kq, but now the distance, we've got the d on 2 here plus the x. So we've got d on 2 plus x squared, and that's to the right. And for the charge at d on 2, we've got kq, and then the distance here, you can see it'll be this x, but then we have to subtract off this d on 2. So it'll be x minus d on 2 squared, and this is also to the right. So because these are in the same direction, we just sum them. So E total will equal E minus d on 2 plus E d on 2. And so this will equal k cubed, which is a common factor between these two. And then we've got 1 on d on 2 plus x squared. And then we've got plus 1 on x minus d on 2 squared. And so we'll want to simplify this again. So we've got k cubed. Let's give it a common denominator. So let's write this as x plus d on 2 squared, x minus d on 2 squared, and then we've got x minus d on 2 squared plus x plus d on 2 squared. And then we'll want to expand this, so k cubed. On the top, we've got x squared minus xd plus d squared on 4 plus x squared plus xd minus plus d squared on 4. So you can see the xd and the minus xd will cancel, and then this one we can write as x squared minus d squared on 4 squared. So we end up with kq times 2x squared, and then d squared on 4 plus d squared on 4, so that's plus d squared on 2, divided by x squared minus d squared on 4 squared. And then the question asked us to check the limit as x goes to 0. So let's first of all think about that physically. As x gets really, really big, we're getting really far from these 2-point charges. So it looks like these 2-point charges are at the same location. D on 2 is very small compared to x. So what we would expect us to now have a point charge with a charge 2q. So we'd expect it to go towards k times the new charge, which is 2q, and then the distance from this charge is given by x squared. So that's what we would expect physically. Let's check if that's what happens mathematically. So we're now going to take the limit as x goes to infinity. Now as x goes to infinity, the d squared on 4 is negligible. So we've got kq still. The d squared on 2 is also negligible compared to the 2x squared. So we've got 2x squared is what's in this bracket. And then on the bottom, we've got x squared, and this is squared. So this is equal to 2kq x squared over x to the 4, which you can see is equal to 2kq on x squared. So we've got the same expression for the limit which we got mathematically as our physical expectation would be.